to start, because the practice starts. That you need so bad. Problem is the following. Oh yes, I really like the internet in Hungary. Here we have this practice. No, not here. Not here. Well, this is really important. Well, actually, you learned this last semester, so it is not so disturbing that it is in Hungary. However, this is disturbing. Very disturbing. And this is much more disturbing. So, what can we do? More or less nothing. I'm really happy that I have 3 different accounts. So, okay, sorry. So I will translate. These are in Hungarian and I had no time. Actually, I had time, because I had no internet, to translate it to English. So, first, this is some quantum mechanics. Okay, so the power of the light source is 75 watts. Questions. How much is the frequency of light if the full energy of the light source is emitted? How many photons are emitted per every second? So, okay, question A with one word. Bullshit. So it asks for the frequency of the light source. Okay, not 100% Vs, because it is given the wavelength, but from the wavelength with one operation we can calculate the frequency. So I don't know. Anyone else broke the chalks like me? So this is the what you can see. This is the power. We have I can write but here it has no importance in draw, so this would be a valve or something like this. Okay, so the frequency. What we know, for all waves, the propagation speed is the wavelength multiplied the frequency. So the frequency is c per lambda. C is 3 times 10⁸ meter per second. The lambda is, wait, here I forgot to write something. Yeah, I forgot that one. The light source is emitted by and here then and that's it. That's 6 times 10 power minus 9. So meter, then I have and then that's half. It's not so nice. So this is I hope I'm right. So from the propagation speed of the light and from the wavelength of the light, we can get the frequency of this source. How many photons are emitted from this light source per second? We have the frequency, great. We know the Planck constant, great. We can calculate the, what is the name, the energy of one photon, and then we can get the number of photons. So one photon's energy is this one. The Planck constant is something 6.6 something like this. Where is it? Yeah, it's here. I have the frequency from here. Nice number, okay? And this is not hertz right now, actually, but I can say it's hertz. So this is the number of the photons. The mole number is 6 times 10 over 23. So it means, well, it's a large number. It's okay? Actually, we should have started with this and not with the photon stuff. Just, well, I thought you had such exercise in the first, nothing? Okay, sorry. Okay. I will not go through perfectly on the second exercise. Just I translate it and explain you. You can check this at home. So, how many photons are emitted by 0.7 milliwatt carbon dioxide laser if its wavelength is 10.6 micrometer? I will write this down, but question, what is a laser? Do you know what is a laser? Disco, or dance, or everything. So what is a laser? I will explain you later in lecture, but do you have any idea what is it? Yes, please. Yes, and what are its the special features of these light particles? What are their color? It's the same. It's monochromic, and also it's coherent. So the phase is also in the same. So the laser is monochromic. In a normal light beam, there are more different wavelength photons, and therefore there are some dispersion and a lot of bad things. And also the phase of the light waves are the same. So you can use it as pointer, or if you build a Death Star, you can destroy planets. Okay, not really, but you really can cut with the laser, or point, or you can do a lot of things with it because it's not coherent. The normal stuff, normal light, refractor is go and it's a wider beam, but with laser it's a tight beam. You can even target the moon and return from light from the moon. You can do it with a normal light, but the signal which refracted is so weak that you cannot detect it. When the Apollo mission went to the moon, they left their mirrors. And with these mirrors and lasers, we can determine the distance of the moon from the Earth. It changes. The orbit of the moon is extremely difficult, actually. It is determined the Earth, the Sun, and the Venus, and sometimes by the Jupiter. And the Jupiter is quite far. I have a BSc in computer science, and I wrote a planetary program, and I used a very simple approach to determine the position of the orbits. It was quite simple. I applied the same for the moon, but it did not work. So I had to ask a 1,000 row long code to calculate. Never mind. Here, you have laser, and the question, how many photons are emitted by this laser if its wave length is out. Okay, so we have the laser. The power is out. Sorry. I need the change because we don't use microwatts and micrometer and other stuff. The wavelength is micro means 10 over minus 6. So I switched it to, changed it to meter because that's SC. And the question is the number of photons. It is a very similar task like the previous one, so I will not do everything, just this number of photons is the power of the laser divided by the energy of one quantum. We don't know the frequency of this, but we will know very soon, because this is nothing more just C per lambda. You remember, I hope you remember, from mechanics. So the propagation speed of the wave is the frequency and the wavelength. So, well, actually I'm almost finished, so I can finish it. I really like it. It's -8. -36, so it's +18, that's okay. And then there is no dimension. You know, in physics, everything has a unit, and the unit you can check the results. So, what I have here. Big mess. Not mass, mess. Okay, it's not a very ugly number. Oh. Still quite a large number of photons. Okay, let's see what we have right now. Okay, I think we have a break. Okay? 10 minutes. continue. Let's carry on. Okay. So there is a 20 joule laser. The power, so the energy of the laser is 30 joule, and the one impulse needs 510. No. I think this should be 500 This is very bad. This is very bad. Oh, okay. We are booking this. I know what I thought. Okay, so we have a laser. Energy is 20 joule, and the length of its impulse is 5 times seconds. The wavelength is 580 nanometers. And radiates metal how much is the power of the laser? Question B. How many photons is in one impulse? See how what is the maximal speed of electrons if the work that needs to kick off them is this. Okay, so we have this nice exercise. Great. Well, no, I don't know how I will write, but I will somehow. So what is it? We have a laser. The laser has a mirror, a semi-transmitting mirror. There is a gas or a crystal inside, and it injected. So it's always, because the laser must go through and back, radiates in impulses. So if you see that the laser energy is 20 joule, then that 20 joule is come from from this 5 times this 500 nanoseconds. So to calculate the power is very simple. To divide the energy by the time. Second question is how many photons are in the impulse. The wavelength is given. Based on the wavelength, you can calculate the frequency. Based on the frequency and the Planck constant, you can calculate the energy of one photon, and then you can calculate the number of photons. C. What is the max speed kick of electrons if you need this amount of work to leave this plate? This is the only challenging stuff, but we had done such exercise before. So that's it. I cannot write properly, it doesn't matter. We have laser. It emits a metal, and one photon comes and kicks out electrons. This is the photoelectric effects. So about the laser, we have energy of one impulse 20 joule. The period is this time. That means, well, it's good, but for us it's not nice because it's not essay, but I just wrote this down. The wavelength is 580 nanometer. That means this, I just wrote this, change this to SC. The questions are the power, the number of photons, and the speed of the electrons. Okay. First, A. The power is nothing more than energy per time. That's 20 joule per that's 4 hours. Joule per second. Okay, that's easy. B. Number of photons. So the number of photons came from energy per the energy of one photon, and that's come from energy h c per lambda. Everyone knows it's 20 joule. It's there's the length. This is the bond constant. And this is the speed of light. Joule, second, meter. So the result has no dimension. What it has? It has something. And that's minus 26, above it's minus 26, minus, let's define right. Yeah, it's okay. And then I have to calculate this number. That is very challenging task. Okay, not bad. So that's the number of the photons. It is emitted in every, I don't know, half milliseconds. Okay, you know this, and we did this because of this C. This C is the question. So, what is the speed of this electrons? So, what happens? The photon comes, then the electron leaves, but it must leave this. So there's a work out. So this is how the metal bonds the electrons, and then you have kinetic energy. The question is this, VA. So it means and we have here not a frequency but a wavelength. Okay. This will be okay. So what we have? We have the wait. I forgot to write this down. This V out, and you didn't tell me. That's 3 times this one. Okay, then not so well. So for then okay, yeah. see what we have. We have meter, second, and the outcome will be meter per second. That's great. Otherwise, the situation is not so great. Very close. This is minus, this is minus 26. Okay, that's minus, okay, that's, sounds better. Okay, so this is it's not so elegant, but if I don't make so many mistakes, then that's the result. So with this laser, we radiated this metal plate, and then the electrons will leave it with approximately 300 km per second. That's fine, because when we did something similar, we had 1,000 km per second. But I might make mistakes. We will see. So, okay. Okay. Exercise 4. What is the energy of the photon of 0.1 nanometer wavelength X-ray radiation in joule and electrovolts? What is the impulse and the mass of the photon? I have to write it down, sorry. So, you will got this in English. So, what is the okay, so we have nice X-ray photon, Röntgen in Hungary. The wavelength is questions energy, units joule, electrovolt, impulse, and mass. So, first, energy. Energy is Planck constant times multiplied by frequency. That means Planck constant C per lambda. It means seconds, meter, So the result will be in joule. That means this is minus 26, 10 minus 16, 16, yes. And this one is this is so this is one result, I hope so. Wait. No, it's, oh yeah, yes, thank you. It was suspicious. Okay, so this is it. What is the electrovolt? The electrovolt is the energy of one electron accelerated by 1 volt, and the charge of the electron is 1.6. If I remember well, 1.6 times 10 over minus 90. So it means that okay, so 1 electrovolt is approximately so this one is oh, that's bad. So, the difference is 4 order of magnitude. So this one is something I hope so. multiplied that one with this, I got that one. Okay, so this is the answer for the first question. The next one is what is the impulse of this? And here P comes from, this is the de Broglie equation. That's here. So actually this is the opposite, but we'll do it. So the length of a particle with P, I mean P impulse, is this one. So this is the Broglie. So the impulse is h times wavelength, and that was, oh, it's easy to calculate. No. Sometimes I want to write something and I write something else. This is not that one. This is this one. And this is kilogram times meter per secondum on square times this one. So it means this will be something is not good. Something is not good. So the Broglie length something is not good here. So this was the wave of this one. That one. No. No, yes. No. Oh, I know. Okay. Yes. Sorry. H per P. So from this is the P is from H per length. So this is and now the dimensions are fine. This is kilogram per meter per second, that the impulse, and this one is so this is it. And now I have 2 minutes or 1, and the most important part comes the mass. The mass comes from the Einstein's famous equation. Please wait for it and then we can leave. Please, and everything. So the C is the mass of this Röntgen photon, or I mean X-ray photon. Energy is M times C squared. We know the energy is also H times F. Or H times C per lambda. Yes, so with C I can do this, and then the M is nothing more than H lambda C. The length, how much was it? It's yes, 10 minus 10 meter, 3 times. Okay. This is kilogram meter. Okay, so this is kilogram times meter square per second square. That's okay. The second disappears. The meter also disappears, so the result will be in kilogram. And that will be minus 30. Minus 34, then it's minus 24, and that's and this is the new information. This is the mass of this X-ray photon. It's quite small, very small, and that's it. Thank you very much. We will continue this next time. Short lecture, longer practice. Thank you very much.